Have you ever wondered what really makes this light bulb glow? We all know we need electricity, but what's actually pushing those charges through the wire, that invisible push, that force, is what we call voltage. It's not just a number on your battery, it's the pressure that makes electricity flow. In this video, we'll uncover what voltage truly means beyond the textbook definition. You'll see how it works in real life, why it's compared to water pressure, and how this single concept powers almost everything around you, from your phone to rockets. Welcome to Gears to Gates. This is the first video in Basics of Electronics series, inspired by Art of Electronics. In this video, we're going to build a clear, intuitive understanding of voltage using a simple, day-to-day analogy of a water tank and its elevation. After that, we'll break down the definition of 1 volt, a concept based on energy and charge. To make it relatable, we'll look at what 1 joule of energy really means in everyday life and get a feel for what 1 Coulomb of charge represents, again with simple, real-world comparisons. We'll then move on to understand current and finally wrap up by defining power and seeing how it connects voltage and current together. Let's begin by understanding voltage through a simple and familiar analogy. Imagine you have a water tank placed a few meters above the ground. We all know that the higher the tank, the stronger the water flows when we open the tap. For example, if the tank is placed at a height of 3 meters, the water might flow at about 10 liters per minute. But if we raise that same tank to 5 meters, the flow could increase to 13 liters per minute. So what changed? The potential energy of the water increased. By lifting the tank higher, we've done work on the water. We've given it more potential energy. And that extra potential energy shows up as a stronger flow when the water comes out. To be noted that it is actually the difference in potential that is driving the water flow and not the elevation of any one of the points. Meaning, if we reduce the difference in elevation between 2 tanks by raising the tank on ground to 2 meters elevation, then the difference in elevation is back to 3 meters, and the flow rate would reduce to 10 liters per minute. Thus, it is emphasized that the difference in potential, or the difference in elevation between 2 points, is of importance than the individual elevations of the points. Now, let's carry this idea into the electrical world. Here, instead of water, we have electric charge. Think of it as countless tiny particles that can move through a wire. The height of the tank is now replaced by voltage, and the flow of water becomes the flow of electric charge, which we call current. Just as the difference in elevation causes water to flow, the difference in voltage causes electric charge to flow. In other words, difference in voltage is the driving force that pushes electrons through a circuit. Greater the voltage difference, greater the electric current as seen in this animation. Now let us try to understand what is 1 volt. Okay, let's start with the textbook definition. Just for a second. Imagine 2 points, A and B. If it takes 1 joule of work to move 1 Coulomb of charge from A to B, then we say that point B is 1 volt higher than point A. Or in other words, the voltage difference between A and B is 1 volt. All right, sounds nice, but also a bit boring, right? Let's bring it to life. Think about 2 magnets. When you try to push the north pole of one magnet toward the north pole of another, you can actually feel that invisible pushback. You have to do work to bring them closer. That's the main idea here. Just like magnetic materials feel a force in a magnetic field, and things with mass feel a force in a gravitational field, anything with charge feels a force in an electric field. Now imagine you're moving 1 Coulomb of charge from a point of lower voltage to a point of higher voltage. If that takes 1 joule of effort, then those 2 points differ by exactly 1 volt. Simple. But hang on. What's 1 joule of work? Let's relate it to something real. When you toss a cricket ball gently in one hand like this, that tiny effort you put in, that's roughly 1 joule of energy. So next time you toss a ball, you're basically doing 1 joule of work. If only the ball were a charged particle, you'd be making voltage. Now, what about 1 Coulomb of charge? A Coulomb is technically same amount of charge as collective charge of 6,240 quadrillion electrons. But how to see in day-to-day perspective? Here's a cool example. A typical phone battery, say around 5,000 milliamp hours, can store about 18,000 coulombs of charge. So, if your phone battery drops by just 2% while watching this video, you've already used up roughly 360 coulombs of charge. That's thousands of quadrillions of electrons flowing invisibly through your phone. All right, now that we know what charge is, let's talk about current. Current is simply how fast the charge is flowing. Basically, the rate of flow of electric charge. So if 1 Coulomb of charge passes through a wire in 1 second, that's called 1 ampere of current. Think of it like counting how many charge packets pass through a point every second. And now, everything connects beautifully with power. We already know voltage is work done per Coulomb, and current is Coulomb per second. Multiply them, and what do you get? Work done per second. That's instantaneous power. How fast work is being done, or how quickly energy is being transferred at any given moment through a circuit elements. In the next video, we'll take this understanding a step further and see how voltage and current behave in complete circuits using Kirchhoff's laws. That's where all these ideas really start to come together. If you found this useful, don't forget to like, share, and subscribe, and I'll see you in the next one.